This video is an overview of topics concerning the D block elements and representative questions. Within the first two sets, we're looking at um, different regions of the periodic table and making some comparisons. I like this whole expanded version of the periodic table because it provides some insights for the comparisons. If I'm comparing uh, electrons that would be filling the s orbitals versus filling the ones at the end of the d, similarities within that set because, after all, the valence electrons, if I was talking about calcium, would be in the 4s, and they'd also be valence electrons if I was talking about zinc, because I filled up all the d orbitals, and the d orbitals are also lower in energy than the 4s, so I could see why I'd have similarities there. But the d orbitals themselves are poor in shielding, so we see differences for sure in terms of the ionization energy if I'm comparing something like calcium with zinc. So the key thing here is that we're increasing the number of protons. We're adding d electrons, sure, but because they're poor in shielding, the ionization energy is going up. That gets even more pronounced if I'm looking at something like mercury, because I've also then added preceding f orbitals, which are poor in shielding as well. This is what we described as the lanthanide contraction. It's linked to this other question about the element mercury having similarities with a noble gas. If we look at mercury, even though it appears to be and is right in the middle of the periodic table, within this representation we see that we have filled up the s orbitals, the f orbitals, the d orbitals, and so it has a closed shell description similar to a noble gas. Adding to that, the valence electrons, the 6s, are held closer to the nucleus because of the poor shielding that we had regarding the lanthanide contraction, and that's even more magnified in terms of relativistic effects. So for all of these reasons, even though mercury is shown here in the middle of the periodic table, the kinds of interactions it has between mercury atoms resemble those that we have between noble gases. Within this one, we're looking at X-ray diffraction. What type of experiment is shown? I'd be looking at two different features here. So based in terms of the detector setup and the output, this is a polycrystalline sample. It's not a single crystalline sample. We have the incident ray and the detector. What's constant in this is the wavelength of the X-ray coming in. We're varying the angle between the incident ray and the detector. And our goal is to get insights in terms of the d-spacing, which is the spacing between the different planes within the crystalline structure. That's what's giving rise to our constructive interference. If this had been a single crystal, the output looks quite different because we're getting information not just in this one angle, but from many different angles. This is what allows us to get the overall crystal structure determination, a single crystal. With an amorphous one, we have much less information. At the top here, this would be an example of a crystalline sample, polycrystalline sample with powder X-ray diffraction. To consider what the profiles look like when we're having an amorphous sample, we really lose a lot of information as the disorder in the sample is leading to very broad lines. This one considering aluminum chloride being acidic. In a general way, we've seen when we have now small highly charged cations, they would get coordinated by the water. That would be a great example of the ligand acting as a Lewis base, a electron pair donator. In the process, the water that's now being coordinated, the oxygen-hydrogen bond is affected within that molecule, weakening it, allowing the donation of a proton to the surrounding water. This would be a great example of a Bronsted-Lowry description where we have a proton donor and the water acting as a proton acceptor. Looking at Alfred Werner's work, if you recall, he was addressing this type of question where this would have been the notation that is given for this cobalt complex, where the thought was that cobalt, if it was plus 3, due to its valence, it could have 3 different bonds that would form. This is a very different description than what we've been looking at within the class for a coordination compound. This case, same formula with the cobalt now being octahedrally coordinated, and the chloride also acting as a ligand, with one chloride being found as a counterion outside of that coordination sphere. So the one on the right, that's the description that Werner led to. The way that he would determine things like that, well, what would happen if we added silver ions? Well, the silver ions could lead to a precipitate silver chloride. This would provide us into insights where the chloride ions were located. In this particular case, I would have one chloride that would be not tightly bound to the structure. This chloride could be involved then in the formation of the silver chloride. If you had a different structure that had two chlorides as counterions, then the amount of the silver chloride that formed would be different. So he did experiments like that, determining the amount of a precipitate that would form, doing measurements involving conductivity. These were all providing insights as to whether different ions, different ligands were coordinated to the metal or found outside of it. And that's what led to this view of complex ions. As an example of a complex ion here, this would be taking the formula and making a picture for what's being described. I've shown it here in a trans geometry with the OH ligands across from each other. Within the coordination sphere itself, we have 4 ammonias, 2 of the hydroxides, and then outside of the sphere, the counterion, which would be the bromide. If we're looking at different types of isomers that we could have, if we had the bromide replace one of the ligands like the ammonia or the hydroxide, that would be an ionization isomer. Hydration would have water replacing one of the ligands. A linkage isomer, I don't think that's possible. A linkage isomer would be taking one of the ligands currently found here and changing its orientation, flipping it over. In each of the cases, the part of the ligand that's coordinating to the metal, the lone pair is found on the nitrogen or on the oxygen. That's the only way that ligand can be coordinated. So I don't think a linkage isomer would be possible. We see this description of what would it mean to have stereoisomers. I've drawn this one here in a trans arrangement. I could have also written it in a cis arrangement. So I have 2 different ways that I could put it together. So I'd call that a geometric isomer. I call it a geometrical isomer and not an optical isomer because if I were to take the mirror image of this, it would be superimposable on the original. If it was not superimposable, that would be an optical isomer. I don't think an optical isomer is possible. If you can sketch one and prove me wrong, have at it. But I don't think you can have an optical isomer in this case. Looking at the same description here and considering crystal field theory and looking at the magnetic properties. So I want to first identify this is cobalt 3+ with 6 d electrons. If we're then placing it into an octahedral field, what we end up finding is that we have a splitting into 2 different sets by T2G and the EG as we have the ligands approaching. Here's an equation describing the spin-only magnetic moment. So if I'm looking at this in a high spin arrangement, I'd have a total of 4 unpaired d electrons. If I were to look at this in a low spin, all 6 would be in the bottom, and I would have 0 unpaired electrons. So I have a dramatic difference in the magnetic properties. In one case, because I have 4 unpaired electrons, in the other case, it's diamagnetic with 0. On the topic here of that chelate effect, the idea here is that if we were to replace the ligands with something that's bidentate, polydentate in some way, we end up increasing the total number of particles that are in solution. Right here on the left, I see 1, 2 different particles. On the right, I have 1, 2, 3. I've increased the number of particles that are in solution when I've had the bidentate or polydentate ligand replace what was initially there. So that's explained thermodynamically in terms of increasing the entropy. Increasing the number of particles, we're increasing the entropy. It's not involved significantly in terms of the enthalpy, because in each case, I still have a nitrogen here being coordinated to the copper. whether it was with simply the ammonia or within the bidentate ligand. Key difference here is the overall entropy increased, and that's what's leading to a very favorable, a very large Kf value. Considering this, whether the complex is chiral, I made a sketch of this. I looked at the mirror image of it, and I thought, could I somehow spin, rotate, and return it back to the original? So here I rotated it, spinning it around the central axis. That's not the original. Here's one where I rotated it by flipping the top to the bottom. That's also not the original. So this would be an example of something that's not superimposable, which means it's chiral. What does it mean to include a bidentate ligand? Could you have that be chiral or not? So here's a few different examples. So with this line, I'm indicating that as a bidentate ligand. I had the mirror image in this case. In this one, I could then spin it around the central axis and return it back to where it was initially, so that would be superimposable. Same with this particular one. I could then spin it around and return it to where it was originally. This bottom one, as an example, would be non-superimposable. When I look at the mirror image, no matter how I could spin it, rotate it, it wouldn't return to the original. If we're comparing and contrasting the crystal field splitting for octahedral and tetrahedral, different comparisons that you can make. The initial phenomena is the same in each case, but in the octahedral example, we have the ligands approaching along the x, the y, and the z axis, leading to this particular splitting. If the ligands approach off of those axes, then instead of having the arrangement being octahedral, that's describing our tetrahedral. So in both cases, we have a splitting into a lower and a higher energy level. In terms of the octahedral, the T2G is lower in energy than the EG. That's a notation given when we have these 3 and 2 different energy levels. With the octahedral, those are just flipped over. Another feature within that in terms of being flipped over, there's also a smaller difference in the splitting. And that's noteworthy because it means that the tetrahedral is always going to be in a high spin arrangement, whereas with an octahedral, depending on the crystal field splitting, you could have either a high spin or a low spin complex possible. Looking specifically here at manganese 2+, so that's said to be coordinated by 4 ligands, so I'm thinking tetrahedral. If it's tetrahedral, it's always going to be high spin. If I were to consider the magnetic properties, if I change the ligands, if it remained tetrahedral, I'm not going to change the number of electrons that I have if I change the energy difference, because it's going to remain high spin. I would have 5 unpaired electrons in both cases. If I were to think about changing the strength of the field and the color change, if it's tetrahedral, I'm still going to be describing it as a tetrahedral that's high spin, but the energy difference will actually change if I'm changing the nature of the ligands. So I'm not saying that it's going to switch between high and low spin. It could retain and stay high spin, but if I change the difference in energy between the 2 sets of d electrons, the d orbitals, it will then change the energy of the photon that's being absorbed, and it would change the appearance. This is looking at the same kind of description, but now using ligand field theory. I see a lot of similarities in this region right here. Whether I look for an octahedral complex using crystal field theory or my ligand field, I still have the same T2G and EG energy levels. What's being added to when I go to the ligand field theory, it allows me to explain the placement of a given ligand on my spectrochemical series. That's the main achievement, the main thing that it gives me. If I wanted to explain whether, or make predictions as far as whether the magnetic properties are a certain way, if I want to make a prediction as far as if I change one ligand to another, how it might affect the color, both crystal field theory and ligand field theory, they're both quite suitable. The main difference here is that ligand field theory helps me explain a series that I might otherwise have established just with experimental data. In ligand field theory, if we look at this, we have examples of non-bonding molecular orbitals. They were with the D on the 3D on the metal, and they are now non-bonding because they are not directly overlapping with the orbitals that are on the incoming ligands. That's really consistent with what we saw with crystal field theory itself, where we had our lower in energy, our T2G, because they were not directly along the XYZ, which is where the incoming ligands were. So this idea of having lower in energy because they were not directly aligned with the incoming ligands, that's exactly the case in crystal field theory, and that's what's making them designated non-bonding, because there's not an overlap between the metal's d electrons that are in those atomic orbitals and the atomic orbitals of the incoming ligands. Finally, if we're thinking about UV-Vis spectroscopy, what could lead to broad absorption lines? Well, first of all, what would lead to very narrow lines? If I had simply gaseous atoms, in that case, I have only electronic transitions taking place, which lead to very narrow lines. An example of that would be with our flame atomic absorption spectrophotometry, or FAAS. If instead of having gaseous atoms that are now molecules, well, now more things can happen. Besides just having electronic transitions, I could add in different rotations. I'm adding other types of motion besides simply the electronic transitions, which is now going to broaden the lines. It gets dramatically more broadened when I look at now in solution. Because yes, I have electronic transitions, but now I have molecules bouncing into each other, interacting with the solvent. There's a lot more things that the energy can do after it's added to the molecule. And if I have a lot more things that the energy can do, instead of having these very narrow, discrete lines, it gets broadened out. And we see that within our UV-Vis spectroscopy, when it's in solution, a line is certainly not simply 1 nanometer. It's in tens of nanometers. It's much, much broader. And that changes the amount of information we get with our analysis.